this is where the course gets really fun. So we get to put a bunch of things together now that are really nice. I'm going back to this little diagram just so that, you know, I think every time we transition into a new phase of the course, I'll bring it up and kind of show us where we're at. By way of review, we started out looking at over here the idea of kinematics for particles, which was this foundational element for anything that had to do with kind of particle motion and describing particle motion. Then I think from there we went on and we looked at the things that influence or cause particle motion, and that's kinetics up here. So first kinematics, then kinetics. The next thing that we went on and looked at was how to transition into describing motion for bodies that are larger than particles. And so we had to deal with both translational effects as well as rotational effects once the body got larger. And what we're going to add today is the idea of trying to look at influences that cause motion for those larger bodies. So we're kind of dealing with that little block up there in the very back. And we're going to add not only this, relationship that F equals ma, but another relationship that's very related to it, and that is if you look at all of the moments applied to a body, it's equal to the moment of inertia times the angular acceleration. All right, so that's kind of the other relationship that's very similar to F equals ma, and we're going to add that in for today. So that's where we stand. Once we get done with that, then we'll get into these other methods like work and energy and impulse momentum, but we'll save that not for today, but for later. We'll probably spend a couple of lectures at least on this back orange block back there where we're dealing with kinetics for rigid bodies. All right, so let's talk about angular kinetics here just a little bit. And I am gonna spend a few minutes and try to come up with where this concept comes from. And we'll do it by first drawing a little figure where if you imagine having two different masses, okay, I'll call that M1, and over here I'll call this M2. And let's say I have them such that they are connected with these massless rods to some swivel that's in the middle. So there's, maybe a bearing or something that's supporting these things here in the middle. All right, and what we want to kind of think about is, well, first of all, let me say this. They are, let's say we know how far these lengths are. So let's say this is L1, and this is L2. Okay. And what we want to try to figure out is under the influence of a moment or torque, okay, that's trying to make this thing begin to spin, I'll just call that M, what will the response be, okay? And based on what I put up there just a second ago, you might have an intuition that would tell you the response is going to have something to do with this angular acceleration, which we'll call alpha. So if we apply this moment, then we expect that it's going to respond by this thing is going to begin picking up speed by spinning around that pivot point. So that's, I think, not too far a stretch to think that that could begin to happen. Okay. Well, there's a couple things we can do there. So the first thing that I'll kind of help us think about is how does that moment actually transmit into the masses that are on the ends. And so the first thing I'll do is just show just the little massless rod. Okay, so the little massless rod is here. We're putting this moment of M on the massless rod. Okay. If it is a massless rod, then what it will do under this moment of M is it will accelerate uncontrollably, because you actually imagine this, there's nothing to slow it down. There's no mass that it's actually accelerating. And so that must not be what's really happening there. What's probably really happening instead is that there are reaction forces that react against this moment, okay? And each of these masses contributes to the reaction against that mass. And so where this thing would want to begin accelerating in a counterclockwise sense, there's probably going to be some reaction force here, and I'll just call that F2, and there will be another reaction force over here, okay, that we'll call F1. All right, and keep in mind that we still have these lengths L1 and L2. All right, and let's say that, you know, basically each of those forces contributes to this moment, such that I could say here that the moment is equal to an M1 plus M2, which is just going to be equal to F1 times L1 plus F2 times L2. Do you agree with that? So what we need to do, it is probably a good idea to think about the signs, but what we can do there is if we imagine summing moments around the pivot point, M would be positive, right? And F2 and F1 would both create negative moments because they would be trying to turn it clockwise. Well, once I put those on the other side of the equation, they become positive because they would have been negative, right? So, you know, I did it less formally than that, where you can just sort of see that that is the direction that would balance out M, right? So therefore, the M is equal to the sum of those two moments. All right? Well, so far so good, but that doesn't actually get us as far as we need to be, because we need to think about how those forces actually interact with M2 and M1. So let's actually think about little diagrams of those. Okay, and I'll do two of those little diagrams over here. Here's M2, here's M1. If F2 is the force that's being applied to that little massless rod, then that means equal in magnitude, opposite direction would be what's applied to this M2, right? And so this F2 that we're dealing with right here, right? That's what we have for that little force. All right. Well, how does M2 respond to that force? All right. Well, I would say that it's going to have some kind of an acceleration, right? Under that force of F2 that's being applied to M2, it's going to want to accelerate. Right? And I'll just call that, I guess, A2 for right now, right? But we want to do more than that. So A2 can actually be related to the alpha that I drew on my little original rod, right? How does A2 relate to alpha? All right? Keep in mind, that's basically like a tangential or a transverse component of acceleration, and to get that, you take your angular acceleration and multiply by a radius away from the point of pivot, right? So this is just going to be equal to alpha times L2. Okay. Can I relate F2 to the moments that I was dealing with earlier? Right? In other words, this M1 is this, and this M2 is this over here. So if I basically say, down here, let me just say F2 is going to be equal to what? M2 over L2. And, may as well do the other one as well, F1 is equal to M1 over L1. Okay, so I'm going to put that up here, that this is just equal to M2 over L2. Okay. Same basic thing works with the other ball, even though it's going in the other direction. And by the way, I should have said this at the very beginning. Let's basically ignore gravity. We'll say it's, at least for this little example that we're doing, we're going to assume we're not in gravity. All right. So what happens with M1 is that it might begin to accelerate this way. A1 is going to be equal to alpha L1, and it's doing that under the influence of this force, F1, which is just equal to M1 over L1. Okay? Well, Newton's second law, we can kind of use that for either one of these cases, right? We can say that F equals ma. In other words, F2 is equal to m2 times a2. Right? Well, if that's the case, then we can say m2 over L2 is equal to m2 right, and then alpha L2. Okay? Or we can kind of recollect this in a little bit different way, and we can say that m2 is equal to L2, let's say m2 L2 squared alpha. What do you think we're going to have for mass 1? There's no reason it should work any different. Mass 1 is just, or the moment, the contribution to the moment m1 is equal to mass 1 times L1 squared alpha. All right. Well, now let's actually use those pieces, right, back with our original thing and say that m is equal to m1 L1 squared alpha plus m2 L2 squared alpha. We can factor out the alpha, and we can say that m is going to be equal to m1 L1 squared plus m2 L2 squared. All this times alpha. Okay, well, so what? All right. We did a lot of effort there. Basically, what we found is that each little particle of mass, if we have a system of particles of mass, each little particle of mass contributes to this thing that is called a moment of inertia. All right, that's what this thing is right here, I. Moment of inertia. Sometimes people will call this the mass moment of inertia. Why do you think they refer to it as the mass moment of inertia? Well, it's partly because in a lot of statics classes or mechanics materials classes, people will start calling what's really called a second moment of area, they'll start referring to it as a moment of inertia. And the reason why is that it's very similar in nature and in mathematical construction to what we just figured out right here. This though is the actual moment of inertia, and sometimes to make sure that people know that that's what we're talking about, people will add the word mass moment of inertia, the word mass in front of it, so that people know that that's what we're talking about. Okay? What if I had more masses? This is actually where this, m is equal to I alpha, right? And this is for a system of two little tiny particles of mass, right? That's one of the things I probably should have said at the beginning. M1 and M2 are considered to be very, very tiny. So tiny that it takes basically zero effort to get them spinning, themselves spinning, right? They're so tiny, they're like particles. All right? Well, so what would happen if there were more of them, more of these little particles? Could I kind of expand this and say I is kind of like a sum? Let's say I have I particles, and I'm summing up all these particles, not I particles, N particles, and I'm summing them up with this index I, right, over M sub I, L sub I squared. Would you agree that that's something that I could probably do if I had a number of discrete particles where each particle was small? Okay, well that's one way to do it. But what happens in real world situations a lot of times is that we have mass that's distributed spatially over a volumetric region of some kind, right? So there's this mass where each little particle of mass contributes almost nothing to the overall mass, and each little particle is located in a different location spatially, right? So what happens with this is instead of dealing with it in a discrete format like we show right here, we think of it more as an integral. And that integral is that we sum over all of the region where there is mass. You sum up each of the little, and I'm going to change from L here to R. Why do you think I'm doing that? Well, one of the reasons I'm doing that is that all of my work up here was predicated on the idea that those L's are radius values away from a point, right? The point where it's going to be rotating around. And so I can call all of those R's, and then each little piece has basically zero mass. And we sum that up over the entire domain, and that's where we get our moment of inertia, okay? So this is a good spot for me to show, to kind of really point out. This is very similar to the second moment of area. As a matter of fact, you know, at least if you're using this textbook that we're using, it uses even the same letter that you probably used for moment of inertia when you were doing a statics, mechanics, and materials kind of approach. And for that, it was this integral over an area or a volume, right, of, you know, r squared dA. And actually, if that's how we were doing it, and in this case we're actually using a polar system of coordinates, I maybe misspoke a second ago. I believe in your statics, mechanics, materials course, you used a letter J to talk about that, because it's actually a polar second moment of area is more akin to what we're dealing with this mass moment of inertia that we're dealing with. So anyway, one of the reasons I bring this up is that I don't want to spend a whole lot of time giving you all these methods of evaluating what a mass moment of inertia is, because I feel like that's a little bit of a waste of time given the fact that you spend a lot of time doing almost the exact same math whenever you were doing second moments of area whenever you were in your statics and mechanics and materials class. Suffice it to say, I'll pick out a few things. So let's say here, methods used in statics, mechanics of materials. Okay, because these all still apply, all right? Parallel axis theorem. I will state these. I won't spend a lot of time deriving them or, you know, trying to prove them to you or even doing examples yet. We'll do a little bit of it in an example here in just a few minutes. But the parallel axis theorem for these mass moments of inertia says that if you want to find the moment of inertia about some other axis that does not go through the center of gravity, then what you do is you take whatever the moment of inertia is about an axis that does go through the center of gravity, which the notation they a lot of times use in this book is just put a little g as a subscript for a moment of inertia about an axis going through the center of gravity. To this, you would add a product of the mass of the object you're trying to evaluate multiplied by the distance between the two axes squared. So here's what that means. So let's say you have, some little blob of mass. Here is a little symbol that represents the CG. Okay, that's something you might want to sort of get used to, is we'll use that symbol sometimes to talk about a center of gravity. Something like this. All right. And what we're saying is, if you already know what the mass moment of inertia is about an axis that goes through that point, right? So let's say you already know that, that's IG. And you're trying to figure out what is the mass moment of inertia if you're trying to evaluate it about some other axis, right? Then what you do is you take this distance of d between those two axes, you square it, and you multiply it by the mass of this thing. Okay, so like the moment of inertia around this, that axis just becomes I equal Ig plus m times d squared. We'll do an example here in just a second using that. Okay. What about dealing with composite shapes? All right. So what you do with composite shapes is you literally take the sum of these moments of inertia about an overall center of gravity. So let's say you have a certain number of shapes. You have like a little circle, you have a little square, whatever. And so you have like shape 1, shape 2. There's some axis that represents like a center of gravity. You have to figure out what each of those shapes, what moment of inertia each of those shapes contributes to the overall. So, I would just say it like this: I equal 1 to n of I sub I, and this gives you an overall moment of inertia about an overall center of gravity. Okay? Maybe I'll say it this way. So anyway, again, I'm going to do an example here real quick, but hopefully this rings a bell that you did something like this whenever you were in your statics class. You had to evaluate if you had multiple shapes and you knew what the second moment of area was for each one. All you had to do is figure out what that second moment of area was all around a common axis, right? And then add them all up. And that's what we're going to do here as well. Here's a different idea, one that you're probably not as familiar with. It's called radius of gyration. Okay. What you do with radius of gyration is you understand that there's basically two factors that go into the resistance of a body to begin to accelerate rotationally, right? Those two factors are how much mass is there, and the other factor is how far away is that mass from the axis that it's spinning around, right? So what you do with the radius of gyration is you kind of acknowledge that second factor, the how far away it is, by basically defining your moment of inertia as some common radius k squared multiplied by the overall mass of an object. Here's physically what this means. Okay, this is the reason I bring it up is that radius of gyration is a factor that is given to engineers a lot of times, either in manuals or I don't know, it kind of tends to pop up here and there. It's a good thing for me to mention it. It's a way of basically, if you already know the mass of an object and you're going to try to begin to accelerate it rotationally, you get this second factor of radius of gyration, and it allows you to solve for what the mass moment of inertia is. Or sometimes it works the other way too, where if you imagine here what this k would actually be, it would just be equal to the square root of I over m, right? Meaning, if you know the the mass moment of inertia, and you know the mass of the object, you can figure out what this radius of gyration is. Physically, what it means is what I was about to say. Physically, what this represents is, imagine you could take the entire mass of the object that you're going to begin to accelerate, and instead of putting it in the geometric shape that it was already set up to be in, you imagine taking it and reforming it into a circular ring that is perfectly slender, right? Such a thing can't actually exist. But imagine taking it and forming it into this ring such that this ring has mass of m, right? And it has a radius of r, or in our case, k, because that's what you're talking about. It's what radius would all that mass have to be at so that it ended up giving you the same mass moment of inertia. Okay? So that's what is meant by the radius of gyration. I don't plan on using it a whole lot, but I feel like you shouldn't go through a dynamics class without thinking a little bit about what it means to have a radius of gyration. All right, so then the last little bit of background that I want to talk through is, what does the process look like here a little bit? So the idea of plane rigid body kinetics. Okay, here's what it looks like. Basically, there's two parts, and I've kind of made reference to this before, but we sum up all of the forces, and the sum of all those forces is going to be equal to the mass of the body times the acceleration. But we have to be kind of careful here. This is the acceleration of the center of gravity. Okay? So it's important for us to find where that is, because the sum of all forces acting on a body is equal to the mass of that body times the acceleration of that center, center of gravity of the body. So I'm going to start drawing a little picture over here. Let's say that you have some sort of a body like this. Here is the center of gravity. Something like that. And you can have any number of forces that act on it, okay? Like you can have gravity. That will always act at the center of gravity. That's why it's named that, right? You can have other forces that act. These forces can be, on a surface, right? You can have a force maybe that acts like this. You can have forces that line up with the center of gravity, or they don't have to, right? You can have forces that are applied somewhere in the body of the thing, right? It doesn't have to be on the surface per se, but each of these forces that get applied to the body have a directionality to them, and they get applied to the body. Some of them are going to tend to try to create rotational effects for this body. We'll get into that in the next piece. But what we're talking about right now is, if you add up, in a vector sense, all of these forces that are applied to the body, they will have the effect of causing the center of gravity of this thing to accelerate. All right, but as you might suspect, this is not enough, because the other thing that happens is the body can also begin to accelerate angularly, right? So if we look at that, we add up all of our moments that are created here. And when we do this, we have to add them all up around, at least I'll say this for now, we have to add them all up around a center of gravity, right? And this is going to be equal to the mass moment of inertia about that center of gravity times alpha. And alpha doesn't actually need a subscript on it because an angular acceleration is the same for the entire body. Okay? I can pick any point in this body, and every point in the body is going to have the same amount of angular acceleration because that's a property of the entire body. Okay? All right, and right now we're dealing with this in 2D. Okay, so one of the things I'll say here is that this is translational. In 2 dimensions. Okay, this over here is rotational. And it goes around the 3rd dimension. Okay. Once you get into 3D stuff, this process gets a little bit more hairy. All right. For now, we're going to focus on 2D and try to get our feet underneath us for this, at least for starters. All right. That's all my background. Let's do an example problem, because that's where it becomes actually clear. All right. Here's our example problem. It might take you a second to kind of digest what I'm saying here, so let me talk through it. What I have is a solid cone of steel. Okay. Actually, I forgot to put that up here. The solid cone is rigidly attached to a rod. Let me put that right up here. Both composed of steel. And they're suspended from a frictionless ball joint as shown. So what I'm trying to get at there, even though it's a little bit hard to visualize at first, that cone and rod are swinging in the XZ plane. I showed it in 3D to kind of give you the idea that that is not just a triangular piece of steel, it's a cone-shaped piece of steel. But it's, swinging there in the XZ plane. Okay? The diameter of the bottom of that cone is 8 centimeters. The height of the cone is 16 centimeters. The length of the little cylindrical rod, part of it, is 24 centimeters. And the diameter of that cylindrical rod is 2 centimeters. I'll go ahead and give you this as well. I'm going to basically say ignore exactly how the point of the cone attaches to the end of that rod for right now. Okay? This is, I guess a good point to kind of mention that a lot of times you create a model that's at least somewhat close to what you're really dealing with. And so I'm going to use the model here that we have this little cone that somehow connects at its little point to the end of this rod. Okay? And maybe we're not too far off of what it might actually be if it was, for instance, welded or something like that. All right. So let's see here. The setup is under the influence of Earth gravity, which is directed downward along the z-axis. What we're supposed to do is at this point in time that it's shown, where theta is equal to 30 degrees, we want to find what the reactions are at the ball joint and what the angular acceleration is of this body around the ball joint. Although I don't have to actually specify that. Once I say angular velocity, that's just is what it is. It's just easiest to picture probably around the ball joint. The other piece of information that you need in order to actually do this problem appropriately is that the angular velocity at this instant is 6 radians per second, and that is downward. Okay, I didn't say that, but I'll say that verbally here. Okay, so kind of swinging down to the negative z with an angular velocity of 6 radians per second. So that's the first thing we're supposed to find is the reactions and that angular acceleration. Second part, what we're going to do is try to figure out what the angular velocity is of the cone and rod when it reaches 90 degrees. Okay, this is a completely separate problem. This is not based on the parameters given in the previous part. This is what if you took this assembly, released it from rest when theta was equal to negative 60 degrees. Where would that be located if theta is negative 60 degrees? It would actually be kind of up at a 60-degree angle above the x-axis, right? So if theta is negative 60 degrees, it's up there, and then you let go of it, and you let it swing down. When theta is 90 degrees, that's where it's pointing straight down. We're going to figure out what the angular velocity is of that assembly when it hits that position. Okay? Well, as you might imagine, one of the things that matters a lot to us here is the ability to find our second moment of, I'm used to teaching statics, and so I'm used to calling it like a second moment of area. That's not what we're dealing with here, right? We're dealing with a mass moment of inertia. So that's one of the things that we're going to need to find. And that's really sort of something we're going to need in both parts A and B. So I'm just going to make that its own thing. I'm going to label this as finding the mass moment of inertia about the center of gravity. Okay? To do this, one of the first things I need to do is figure out how much mass we're dealing with each of the parts, right? So like the mass that I have associated with the rod. Okay? So the mass I have associated with the rod, how do I figure that out? Well, I can probably, for steel, I could probably look up a density for steel. And I actually did look up a density for steel. I won't make you do that right now, but I'll say density for steel, which is a lot of times the letter rho is used for density, is just going to be 7.85. And that's in units of grams per cubic centimeter. How does that compare with water? Almost 8 times as heavy as water, right? Water is typically 1 gram per cubic centimeter. So that's kind of interesting. We don't need to know that per se, but you know, just as a matter of interest. So if I know the density, then what I can do is figure out the volume and multiply by density in order to get mass. So that's what I'm going to do here first. How do I get the volume of that rod? Pi d squared over 4 times the length. So it's the area times the length. The length is 24 centimeters. And then I'll have this density of 7.85 grams per cubic centimeter. And then the last little piece that I want to do here is I don't actually want to leave it in grams. I would prefer to have it in kilograms, right? So I'm going to take this, and there are 1,000 grams in a kilogram. Okay. So that would be my mass of the rod. So I'll go ahead and get that put in here. Pi, I'll do it this way. Pi times 2 squared times 24 times 7.85 divided by 4 times 1,000. Okay. And this gives me 0.5918 kilograms. say 519 kilograms. Okay, and because I might want to use that later, let me store it into, I'll just store it into A. To help me remember that, I'll put that over here. All right, how do I figure out the mass of the cone? All right, well, to help us out a little bit, we do have some reference material. This is reference material that will be available to you whenever you're working on your exam. It's also in the very back of the textbook. One of the things you see there is for a solid cone. The formula is 1/3 pi r squared h, where r squared refers to the radius at the bottom, right? So the mass that we have here of the cone is just going to be equal to pi times, 1/3. I forgot my factor of 1/3. I'll just do it this way. Factor of 3 down here. R squared, so r is, again, the radius of that bottom part. The diameter is 8 centimeters, therefore the radius is 4 centimeters. And then h is 16 centimeters. For our cone. Okay, that's volume. Now what I can do is take volume and multiply it by my density, 7.85 grams per cubic centimeter. All right, and then take this, if I want it in kilograms, I can take and multiply by kilogram per 1,000 grams, like so. And now I can take this into my calculator and we'll put in pi times 4 squared times 16 over 3 times 7.85 divided by 1,000. Okay. This gives me 2.104. And let me put that in B. All right. So far those are just masses. Those are not actually moments of inertia yet that we're trying to find for I sub g. So what we want to do now is determine what the contribution is of each of these parts to the overall moment of inertia around g. To get that, I need to know where the center of gravity actually is, right? Because it's not obvious just by looking at it where the center of gravity is located. So that's my first thing, is let me take and I'll actually do a little miniature picture here so that we know what we're talking about. Let's say that this is my body. All right, relative to the pivot point up there. There's going to be some location. It's probably going to be down here somewhere where that center of gravity is located. I'm going to call this length, maybe call it R sub CG. How do I figure out what R sub CG is? Well, here's how it goes. R sub CG, you take the sum of the products of each of the masses of the pieces, right? This is just like you would have done in statics back when we did this back in statics. You take let's see, the radius for the part number 1, right? How far is that? That's going to be 12 centimeters, right? So we'll say 12 centimeters times how much mass we have with that part, the rod, which is going to be 0.5919 kilograms. And add to that, how far is it to the center of gravity of the cone? Now this is a little bit more tricky because I think what it gives you in the back of the book is that you basically are at a height of 1/4 of the total height of the cone, right? So if the total height of the cone, I'll say that's out here, right? Total height of the cone is h. It says that this little bit down here is h over 4. Well, what does that mean you have from the point where the center of gravity is for the cone up to where it joins up with the rod? It would be 3/4 of the height of the cone. Would you agree with that? Up here, this would be 3/4, basically 3h over 4. Okay. So what I'm going to say here then is that the radius to that location is going to be equal to 24 centimeters, because we have to account for the entire length of the rod, plus 3 times 16 centimeters, which is the height of the cone, over 4. All right, that's how you get from the point where we're measuring relative to for r sub cg down to the location of the center of gravity of the cone part of it. That we need to multiply by 2.104 kilograms. All of that stuff I need to divide by the total amount of mass. The total amount of mass is 0.5919 kilograms plus 2.104 kilograms. Okay. So if I actually compute this, here's what I have. I have a fraction where I have 12 times, I believe I had 0.5919 stored in A. And to that I'm going to add this quantity of 24 plus 3 times 16 over 4. And that all gets multiplied by what I have stored in B. And all of that stuff's going to be divided by what I have stored in A plus what I have stored in B. Okay, and that length then is 30.732 centimeters. Or if we want to express this in meters, how much is it? Right, you divide by 1,000. So that's actually what I'll do. Divide that by 1,000. Not 1,000. 100, right? Let me multiply that by 10. Centimeter to meters is a factor of 100, right? So I shouldn't have put 1,000 in there. So there we go, 0.30732. Okay, let me store that into C. All right, well, we haven't done I yet. So far all we've done is found where is the center of gravity located relative to the pivot point. What we need to do next is start figuring out what is the contribution of each of these locations, or the cone and the rod, what's the contribution of each one of those to the overall moment of inertia of the whole thing. So let's actually start with the rod. Okay. Now, the moment of inertia for the rod, let me actually use some other subscripts here as well. The G, when I put a G on here, that is going to be relative to the center of gravity of the whole thing. Okay, and this will be for the rod. What I'm going to do now is look at what is the moment of inertia for the rod about its own center of gravity. Okay, and I'll call that IC. Plus, what we want to do is take the mass of the rod and multiply it by the distance between these two locations squared. Okay, that one I don't know of a great way to denote that, but basically maybe I'll call it DGC or something like that, right? Squared. So let's actually do that out. So what is the moment of inertia for the rod about its own center of gravity? Well, this is the very back flap of your book again has nice tables that gives that to you. The moment of inertia for a slender rod, which this is a good enough approximation for what we're dealing with here. Slender rod is going to be equal to 1/12 ml squared. Okay, so let me do that here. The mass of the rod is 0.5919 kilograms. Okay, the length of the rod is 24 centimeters. And that has to be squared. So I'll tell you what I'm going to do, because I want this to come out in kind of base units here. Let me take 24 centimeters and multiply it by a meter over 100 centimeters. I'm going to take that and square it, and this is all going to be divided by 12. So far, that is the moment of inertia for the rod about its own center of gravity. That's not really what I want. I want the moment of inertia of the rod about the center of gravity of the composite shape. Okay, so what I need to do then is add to this the mass of the rod multiplied by the distance between these two axes. Okay, and here's how I view that. This should be the difference between 0.30732 meters, which is how far it is from the pivot point to the CG of the whole thing, minus how far is it from the pivot point to the CG of the rod, right? Which is just going to be 12 centimeters. 12 centimeters is 0.12 meters. And that is going to be squared. And this is the contribution of the rod to the moment of inertia about the center of gravity of the composite shape. All right, shall we plug this in? I think so. So we'll put it in as, I believe I had that in A, times 24 over 100, right? Which is just going to be equal to 0.24. That will be squared. That's over 12. Plus, okay, here I've got that mass of 0.5919 kilograms is in A. I'm going to take that and multiply it by I believe I had that length of 30 or 0.30732 meters in C. Okay, and what I end up with is 0.02361 units. All right. Easiest to see the units over on the right term over there. It should be kilogram meters squared. All right. We might want to take a second and make sure that's what we have on the left side as well. It looks like it is because the centimeters cancel right here. So that one would also be kilogram meters squared. Okay, and keep in mind, all we've done so far is just the rod. We now need to do the cone, okay, because there's the two parts that make up this overall assembly. So, IG for the cone works basically the same way. We first need to figure out what is the the moment of inertia for the cone about its own CG. All right. So fortunately, we are given that. Also in this page that's on the back of the book, we're given a formula that allows us to find that. Okay, so I'm looking at the cone here. The formula it gives is 3/80 m times 4r squared plus h squared. Okay, so here's what that looks like. 3/80 times the mass of the cone. The mass of the cone is 2.104 kilograms. Okay, times, here I've got 4, I need the radius of the cone. The radius of the cone is 4 centimeters. Okay, do you think I want to keep that in centimeters? Probably not, so I'm going to take this and multiply by a meter per 100 centimeters. That is going to be squared, plus the h of the cone is 16 centimeters, which I'll also multiply that by a meter per 100 centimeters. Okay, all that stuff that I just wrote right there is just the first term to figure out what the moment of inertia is for the cone. This is the term that figures out what it is for the cone about its own center of gravity. To this, I have to add the parallel axis theorem term, right? So I have to take the mass of the cone, which is 2.104 kilograms, times the distance between these two axes. Okay, that distance is going to be equal to, okay, first of all I have to figure out how far is it from the pivot point to the CG of the cone. So for that it's going to be 24 centimeters plus 3 times 16 centimeters over 4. And from this, I have to subtract how far is it from the pivot point to the CG of the whole size of the body. So I have to subtract this 30 centimeters or so, which I'll express this in meters here. Okay. Now, you're probably looking at that and say, I better deal with those units. I agree. I better deal with those units. All right. So what I would say is the easiest way to do that is to take what's in here and multiply by meters per 100 centimeters. Okay. So again, the first big old term up here This is what is the moment of inertia of the cone about its own centroidal axis, or its own center of gravity axis. Okay, and by the way, that axis, I should probably illustrate that for you up here. That axis is parallel with the y, right? So it pierces through this cone right about here, parallel with the y direction. That's the axis around which I'm doing this. So if you're looking at that picture of the cone in the book, that is the direction that that axis goes. It pierces through the cone sideways, right? That's what we have to deal with, because that's the axis around which the cone is going to be rotating, right? All right. So that stuff in yellow right there is the moment of inertia about its own axis. The stuff in blue here is what we have to add in order to get the total moment of inertia about the CG of the entire composite body. All right, we'll plug it in here. So 3 times 2.104, I believe, was stored in B, times, here I've got 4 times, this is going to be 0.04 squared, plus, okay, here we've got 0.16 squared. All right, and all that is going to be over 80. To this, we're going to add, okay, 2.104 I had stored in B, times, here I'll do 24 plus 3 times 16 over 4. All right, and all of that I'm going to divide by 100. And to that I'm going to, or from that I'm going to subtract what I have stored in C and square that whole thing. Okay, and this number that I get right here, it's expressed in scientific notation. That's because it's kind of small relative to what the rod was. That's kind of interesting. Which one's more massive? The cone's more massive, right? So why does it have a smaller contribution to the overall moment of inertia around the CG of the composite body? Why is that, you think? It all has to do with your radius values, right? The mass of the rod is spaced further away from the CG of the overall piece, right? So it's because of that distance, it gets weighted more heavily. So anyway, let's see. I want to store this, and I want to store it into what? Let me store it into E. Okay, I can't remember now if I may have lost the opportunity to store this value into somewhere. I might just have to use the value. I try to be efficient and everywhere I can, but let me just check real quick. Yep, I don't think I had the right thing in there. So, oh well. We'll just have to type it in later. I don't want to spend time putting it in there. All right, so what do I do to figure out what my overall moment of inertia is about the center of gravity of the whole shape? I'll call that just I sub g without any other modifiers. Well, all I got to do is get Ig of the rod plus Ig of the cone. Okay. So I think I had that in E, and to that I must add 0.02361. Okay, 0.0319 8. Is that what it was? Units. This would be in kilogram meters squared. All right, and this one I do want to make sure I don't lose this. Let me store it into F. All right, well, so what, right? We did all of this mess. I even contemplated when I was thinking about doing this problem, I contemplated starting with the equations of motion side of the house, but I figured I didn't want to really interrupt the progress going through that part of it. So we knew we needed to get this value. We've now done all the legwork to figure out what this moment of inertia is about the CG for the body. What we want to do now is the equations of motion. This is, go back up to part A. Angular acceleration of the cone and rod and the reactions at the ball joint. To get this, we want to do equations of motion. Equations of motion arise from free body diagrams and kinetic diagrams. Okay. So let's draw a free body diagram. I'll tell you what, I'm going to put this way up at the top. I'm going to slide myself some room right here, so that way we can look at it. All right, free body diagram and kinetic diagram for part A. All right, and I'm just going to do it as if I'm looking straight down the y-axis. So what I would see if I was looking straight down the y-axis is I'd see this rod. That rod would pivot around some point. I'd have this cone down here. I would have the CG of the cone would be right about here. Okay, and before I start drawing much of anything on here, I'm going to just copy this real quick so that I have the same thing over here for my kinetic diagram. Okay. So for the free body diagram, what sorts of forces act on the free body diagram? Well, one that's fairly easy. It is under the influence of gravity, right? And so the influence of gravity is just going to be equal to the mass of this thing. The mass of it was just, I believe I had that in A and B, right? So, let me just go ahead and put that value on here. A plus B, but that's not a force yet, right? What do I need to multiply that by? Gravity, right? 9.81 meter per second squared. So that tells me I've got 26.451 newtons pulling down as a weight on the center of gravity. All right, what other forces act on this body? Reactions at the pin. Okay, and I'll just call that Rx and Ry. Okay, which kind of means, even if I haven't explicitly stated it, it means I've chosen X and Y coordinates. Okay, and one other thing I want to do is point out that I do know the length of this. Okay. That length, if we go down here, was 0.30732 meters. Right? Did I get it? Okay. All right, so that's one of the things I know, but I also know another thing, and it's based on this problem being at a snapshot in time, right? We're supposed to figure this out when theta is equal 30 degrees. So let me say here that I can say this is 30 degrees. All right. Anything else I need to do for my free body diagram that you can think of? We'll leave it alone for just a second. Let's go over to the kinetic diagram. So the kinetic diagram, one thing we can easily put on here really quick is that we're trying to find this angular acceleration, and that is a property for the entire body. I can just go ahead and put that on there. I can say this thing's going to have an angular acceleration of alpha. That's what I'm trying to find, right? All right, well, but remember the sum of the forces that happen on the free body diagram have to be equal to the accelerations that happen on the kinetic diagram, and they have to be centered at the CG. So let me go ahead and say there's a couple ways I can do that. I can do it in X and Y coordinates, but I think in this particular problem, it's probably easier to state these in terms of a radial component. Okay, maybe I'll call that A sub r, and a tangential or transverse component that I'll call A sub t. And why do you think I'm doing it this way? Okay. The reason I'm doing it this way is it is easier for me to relate those values to alpha if I do it in this set of coordinates. Okay, here's why. I know this length, right? I know the length from here to here is, again, 0.30732 meters. Right? And because I know that length, and another piece of information I have that I'll actually put on here is at this point in time, at this moment in time, this thing also has an omega value, which this is sometimes hard for me to figure out where to put that. I'll just put it over here. The alpha value I put over there, the omega, there's not really any reason I'm putting it here, just I need to put it somewhere. It's 6 radians per second. I'm going to put it like right here. Okay. All right, well, when I know these things, it helps me out because I have kinematic relationships that allow me to establish the instantaneous acceleration that happens of my CG at this point. All it is going to be alpha times my radius. Okay, that's based on the kinematic relationships we went over last time. What about my radial component? Okay, that's from the centripetal effect. That's what's causing that radial component, right? So that centripetal effect then is just going to be equal to omega squared r, right? Omega squared being 6 radians per second squared multiplied by r. All right. So now, how many things do I not know? Okay. I don't know alpha, so that's one of my unknowns. And my x and y reactions that happen at the pin. Right? Awesome, because this is a 2D problem for a rigid body, which means I can do 3 equations, which means I can solve for all of those things, because I can do a system, a 3x3 system, and figure out what those things are. All right, let's start with the rotational equation. Okay, so we sum moments, and we're going to actually sum moments around the center of gravity. Okay, so what I have there is I'll have Ry. Actually, let me start with Rx. Rx tends to rotate the body what direction around the center of gravity? Clockwise or counterclockwise? Okay, it's pulling to the right at a location that's above the CG, which will tend to make it try to rotate clockwise. So I'm going to take this and set it to a negative. Rx, I need just the length from the line of action of Rx to that CG. To get that length, which that is, by the way, the length it would be like from here to here. Right, to get that length, what I do is I take the length, the direct length from the pin to the CG, and I multiply it by the sine of 30 degrees. Okay, so here we would have 0.30732 meters times the sine 30 degrees. All right, what about Ry? Does it tend to go make a clockwise or counterclockwise tendency to rotate about the CG? Okay, counterclockwise, so I would add Ry. What's the length of it away from the CG? Well, it's going to be just the entire length from the pin to the CG multiplied by the cosine of 30 degrees. Okay, so 0.30732 meters times the cosine of 30 degrees. All right, so far so good. What about weight? The 26.451 newtons that I have there. Do I need to deal with that, or is that okay? Okay, so you look at where does the line of action go through? Does it pass through the point we're evaluating the moments around? It does, and so therefore it doesn't tend to create moments around that point. So we leave that term or anything that has to do with that force off of this equation. All right, but we're not dealing with statics, we're dealing with dynamics. So what should this be equal to? Okay, this should be equal to my moment of inertia, I sub g, which was up here. Oh, no, it was down here. I sub g wound up being 0.3198 kilogram meters squared. Make sure I wrote that right. 3198. Okay. That multiplied by alpha. All right. Now, for my other two equations, I don't have to pick x and y. I can pick radial and transverse if I prefer. Okay, and that's actually, I think, probably an easier thing to do here. I'm going to call this my kind of my t-axis, and up here I'll call this my r-axis. Okay, so if I sum forces now, okay, I can choose radial or I can choose the transverse. Let me just do transverse first. Okay. I need to evaluate all of my components of force that align with that t-axis. So first I'll look at maybe Rx. Okay. Rx, it looks like I would need to multiply by the sine of 30 degrees. To figure out the component of Rx that mapped onto the t-axis there. Positive or negative? Okay. Looks like it generally, the portion of Rx that aligns with t looks like it is aligned and not anti-aligned, right? So I would count it as a positive. All right. Then what? We can look at maybe Ry. Okay. Ry, I would need a cosine function. And does it align or anti-align with t? Yeah, so I would subtract. Okay. So far so good. All right. I have one other force that I need to deal with here, and it is weight. So for that one, I would have, it looks like that 26.451 for the portion of it that, coincides with t there, it does align, right? So I would add 26.451 newtons. And I would multiply that by the cosine of 30 degrees, because this will be 30 degrees right here. All right. So what do I set all this equal to? Well, I set it equal to the acceleration in that transverse direction, which is just going to be alpha times 0.30732 meters. That's not quite enough yet. What else do I need? That gives me acceleration that much, and Newton's second law says it's mass times acceleration. So I need to multiply this as well by the total amount of mass that I have of the whole body. And I don't know if I've even written that down anywhere yet. I don't think I have. Let me go ahead and compute that. Before I actually lose this, let me save this in somewhere. Let's see, I haven't used D yet, I don't think. Yeah, I'll use D. Okay, so that gives me that value right there. But that's not what I wanted to deal with. I wanted to do A plus B. .696. Kilograms. All right. We have one more equation to write. We'll sum forces in this radial direction. Okay. So in the radial direction there, I'll start again with x, okay, and it looks like the cosine of 30 degrees will be used to pick off just the component of Rx that is aligned with the radial direction there. What about Ry? Probably need a sine of 30 degrees for that one, positive or negative. Question is, does it basically align or anti-align with the direction I showed there for R? It looks like it lines up, right? It more agrees with it than not. So I add that Ry sine of 30 degrees. All right, what about weight? Looks like it anti-aligns, right? So 26.451 newtons. Okay, but I don't want all of it. I just want the component there that projects onto the R-axis. So I multiply there by the sine of 30 degrees. Okay, and now what's this going to be equal to? Yep, that's centripetal acceleration, which is just going to be equal to 6 radians per second squared times r, which is 0.30732 meters, times what? Mass. All right. So there's our system. Yes, sir. R omega squared. That's basically what I did. Omega squared times R. Right? And then multiply that by mass. Right. They basically are the same. It's the same principle that creates both of those. You know, normal tangential coordinates basically always refer to a path, and it just so happens that the path here is circular. And so the normal direction is radial when you're on a circular path, and the tangential direction is the transverse direction, right? So that all came together just now? Excellent. All right. The good news is we do have some nice tools for us to use. So we're going to use our tools. Okay. So we're going to do a 3x3. And remember, we're putting in our coefficients of each term. So the very first term up here, I'm going to put in a negative. This 0.30732 is actually what I have stored in the variable c. And then sine of 30 degrees. Okay, I am in degree mode. I've checked that real quick. So, all right, so there's the first term there. The next term will be for Ry, so I have positive what I have stored in C times the cosine of 30 degrees. All right. Do I have a weight term or anything like that? Okay, so the weight term would probably end up on the constants side of the equation. I do have an alpha term, right? I need to move that alpha term to the left side of the equation, and when I do, its sign changes, right? So I'm going to put in here a negative, and now I'm trying to remember if I have this value stored anywhere. Maybe go down here and look. I think I do. F, even though I wrote it wrong, I should have put a 0.03198. but I do have it stored in F. So here I'll put negative F. All right. What do I put for this last term? Remember, that's constants, right? Things that are not multiplied by a variable. Do I have anything that's not multiplied by one of the variables? Nope. So I just put in 0. Okay. Next equation here, I put in sine 30, negative cosine 30. All right. Where do I put that weight term? That'll go on the other side of the expression. So here, I want to put the coefficient of alpha. To get the coefficient of alpha, I'm going to, again, take what I have stored in C. Oh, and again, the sign changes when I move to the other side of the expression, so I'll put negative what I have stored in C times, here is actually what I have as the sum of A and B. That's the sum of the two masses of the rod and the cone. All right. Now I take this weight term and I move it to the other side of the expression, which will make it negative. I stored that in D, right? Yeah, D.
For that last one, did you multiply by the radius and the width of the mass?
Did I not do that?
I didn't catch it.
Okay. Let me go back to that one and make sure.
Because A plus B was the 2.696.
Mm-hmm. We'll try this. I think I've got the correct answers on here. So if we try this and it doesn't work, we might have to enter it all again. I don't know why it won't let me.
You have to hit clear first, and then you go back to moving in the matrix.
Will it clear my whole thing?
No, it won't.
All right. There we go. I'll re-enter this just to make sure. So negative, what I had stored in C is that length right there, and then A plus B. Oops. Yeah, that's it. All right, and then over here, I'm going to put in a negative. I had that stored in D times cosine of 30. All right. Now in this last one, we have positive cosine of 30 degrees. We have positive sine of 30 degrees. We have any alpha terms? No, we don't have any alpha terms. So that means I just put 0 here. And now everything else is going to be on the right side of the expression. So I'll start that with the 6 squared times what I have in C times the sum of A and B. All right. And to that I'm going to add what I have in D times the sine of 30 degrees. All right, now the moment of truth has come. Are we scared? We'll say 36.01 for x. What is x? X is Rx. $36.01, what are those units? Okay. Newtons. For Ry, I have 23.74. Newtons. All right, and then alpha will be 24.56. Radians per second squared. All right. Questions at this point? I think we just completed what we needed to for part A. Okay? Before I really finish with part A, though, I'm going to show you one little thing that I think you'll appreciate. If you're dealing with a pure rotational problem, like you have something swinging around a pin, there is a lot of situations where you may not care what the reactions are, and you really only want to know how does that impact the angular acceleration. Okay? There is another way to do it besides doing all this to get that angular acceleration, and it involves finding a different moment of inertia. Okay, we did the moment of inertia, this I about g, we got that value there. What if I did a moment of inertia instead? I'll call it maybe around O for the origin, but it's basically around the pin. Well, what happens there is the only force that creates a tendency to rotate, if you're evaluating it around the pin, is gravity. The reaction forces don't create a tendency to try to accelerate it around the pin, right? So as long as you have a moment of inertia that is appropriate for an axis that goes through the pin, you can more directly find the angular acceleration. So let me show you how that works. Let me call this I about O. I about O is equal to the moment of inertia about the CG plus the mass of the whole thing, right, times the distance between those two axes. What is the distance between those two axes? 0.30732 meters squared. Okay? And what is this IG? Okay? That was this value up here, 0.03198 kilogram meters squared. What I'm evaluating here is a moment of inertia now about an axis that coincides with the pin that this thing swings from, or the ball that it swings from. Okay? And it's going to be significantly larger because it's moving that mass further away from the axis around which I was saying that it's rotating. So let me do this. I believe that I had that first value stored in F, and I'm going to add to that A plus B, okay, times C squared. So 0.2866 kilogram meters squared. Okay, well, what do I do with that? Well, now, when I look at my free body diagram, I can sum moments around this point O. This point O right up here where it's at the origin, basically. Okay, so when I do that, some moments around O, the only moment that I have is just from the gravity, 26.451 newtons. Times, okay, the length that it is away from O, which is going to be 0.30732 meters. Okay, times the cosine of 30 degrees. This is going to be equal to 0.2866 kilogram meters squared times alpha. Right? We basically figured out what that moment of inertia was around the proper axis, and now finding alpha becomes really easy. And it should, if I didn't make any errors in writing that down, should give me the same alpha as I got the way that I just did it. So alpha becomes, okay, 26.451 I had in D, times 0.30732, I had that in C, times the cosine 30 degrees. Okay, to get alpha, I'll divide by this 0.2866, which I believe was my previous answer. And that gives me 24.56, just like I had before. So that gave me a way of finding that angular acceleration without having to do a system. All right? Just immediately got it. I did have to do another parallel axis theorem calculation, right? But it got me straight there. All right. So that is sort of an extra thing for part A, but it's actually a really nice transition for me to go to part B of this problem, and believe it or not, this part B isn't going to take us that long to do. We're supposed to find the angular velocity of the cone and rod at theta equal 90 degrees if it is released from rest at theta equal negative 60 degrees. Okay? Here's what we can use to get that. All right, I believe I touched on this equation. 1/2 omega f squared minus omega I squared is equal to the integral from theta I to theta f of alpha as a function of theta d theta. Okay, so we're starting on part B here. Is there a way that I could write a function for alpha as a function for theta? Where is theta in this last equation that I wrote, the last thing I did in the last part of the problem? Where's theta? Yeah, that's theta right there. That's the only place it shows up. Okay. So, what I can do here is kind of rearrange this a little bit and say that, oh, by the way, based on what the question was asking, it says the angular velocity of the cone rod at theta equal 90 degrees if it is released from rest, right? If it's released from rest at theta equal negative 60 degrees, what does that mean for my omega I? 0, right? So I can kind of rearrange this and say that omega f is going to be equal to, first I'll kind of multiply 2 times this integral from theta I to theta f of, okay, I'll just leave this as alpha of theta for right now, d theta, take the square root of all this. Okay, so now the nitty gritty. Omega f is going to be equal to square root of, if I solve that equation up there in the yellow for alpha, okay, what I actually have there is a lot of that is just constant stuff, right? So I can pull that out there with the 2. Like I would have 2 times 26.45 newtons times 0.30732 meters, okay, divided by 0.2866 kilogram meter squared times this integral from theta I. What's theta I? Negative 60 degrees up to 90 degrees, right? It's supposed to be going all the way down, times the cosine of theta d theta. All right, now, this is actually pretty easy to evaluate in the calculator, with one little asterisk you got to be careful with. I have never had good luck trying to do integrations of trig functions when I'm working in degrees, right? So what I want to do very first thing here is I want to change this to be in radian mode. In radian mode, to get there, we go to Setup, select radians, and now I'm going to enter all this. So square root of 2 times, I believe 26.45 was in D. I believe this other one was in C. And I don't remember storing my new moment of inertia, so I'll just type it in, 0.2866 times my integral, okay? And this is pretty easy too. All you do is just do cosine of x dx. The only thing that's tricky is we got to make it use the correct limits. So I need to convert my degrees to radians. So here I'll probably want to put in negative 60 times pi over 180. And up here I'll put in 90 times pi over 180. And what it gives me there, 10.289, or we'll just say 10.29. Okay. This winds up being in radians per second. So what would you do if you needed to know different limits, like you released it from the very top, for instance? What would you do? You just change this to a negative 90, right? Or if you need to figure it out at the position, like let's say you dropped it from our negative 60 and you wanted to figure out what it was at 30, right at that instant that we were working on a second ago, right? You could do that same thing and figure out what that angular velocity was. I have not really chased those down. I've just tried that a lot of times where I'm using those trig functions, and I stay away from it now because there's been a few times where I thought it worked. I probably just need to sit down with it sometime and figure out what it is that really makes it not work. But I've gotten to the point where instead of doing that, anytime I'm using integration with a trig function in it, I just hop over into radians and do it that way.
Usually what I think whenever I do, I just want to make sure I got this right, that's why I'm asking, is if I leave them in degrees,
Okay.
That works, right? Every time?
It seems to me like it maybe should, so, because that's how that function should work, is that if it's expecting degrees, it should handle it.
Yeah.
Um,
I see
so
what you're just doing what you.
I avoid it because I haven't really figured out why it's burned me in the past, and so just avoid it now.
And then I had another question. Where did you get that equation again? The half omega r squared?
Okay.
I know that's kind of like
That's one of our basic, what it corresponds with is that 1/2 final velocity squared minus initial velocity squared is equal to the integral from an initial position. I'm using I and F here. Sometimes it uses 0, and anyway, I'll use I and F. So initial position to final position of acceleration as a function of position deposition, or displacement, I really probably should say, right? That was the original, I think we even derived that one whenever we started out in this class. I didn't rederive it for angular case, but I basically said, the analogous equation still holds. So that's, that would be the analogous equation to that. Good deal. Well, have a happy 4th of July.